Alright, hello everyone, Brian here, and today what we're going to do is we're going to solve a heat conduction in a bar problem. So what we're essentially going to do is we're going to utilize the heat equation in order to figure out the temperature profile in terms of a spatial coordinate x and the transient time. So this is the basic setup. We have a bar of length L with at x is equal to 0, we have a boundary condition where the temperature is equal to 0. And at length L, we have a boundary condition in which the temperature is equal to 0 as well. Now, as far as our initial condition is concerned, at time is equal to 0, we have the temperature such that it's equal to some generalized function of x. So, with that being the case, I have written the heat equation down below. And we'll go ahead and begin solving this. Okay, so essentially we're only interested in, this is a 1D heat transfer problem with transient properties. So we're wanting it in terms of x and time. So with that being the case, we're no longer interested in the y and z direction because it's not applicable to our problem. So we can essentially just cross those out. Now in this particular problem we have no heat generation, so this q dot term can also go away. Now what that leaves us with, also we're going to assume that this bar is made of a homogeneous material. What this means is that the thermal conductivity does not change with respect to space or time. So in this particular case we can pull out k because we're assuming that it's a constant, and k is the thermal conductivity. So what this gives us is we get k del squared t del x squared is equal to rho Cp del t del t. Now what we can do is we can divide through by rho Cp and we can derive the thermal diffusivity. So that makes this expression alpha. We're going to call the thermal diffusivity alpha. Del squared t del x squared is equal to del t del time. I'm just going to make a special note of this, that the alpha, or thermal diffusivity, is simply equal to the thermal conductivity divided by the density multiplied by Cp, the specific heat. So, we have our given problem. We know that our boundary conditions are as such. We'll just define them here so they're very clear. We know that at 0, for all time t, the boundary condition is for the temperature is 0, and we know that at length L, for all time t, the temperature is equal to 0. As far as our initial condition is concerned, we know that at time, for all x, at time is equal to 0, we want our temperature to have some sort of a generalized function f of x distribution about the rod. So, how do we go about solving this particular problem? What we can do is we can use separation of variables to solve this problem. And separation of variables basically tells us that we can assume that this multivariable function is equal to the multiplication between two functions of each separate variable. So what this basically says, so separation of variables uses, actually let me just write this down here. So we're going to use separation of variables. So this basically tells us that we can make the assumption that our temperature as a function of space and time is equal to some spatial function being multiplied by some temporal function. Now what we can do, so we can take this assumed function using separation of variables, and we can plug that directly into the expression that we derived above. So, let's go ahead and do that. So in doing so, when we sub that in, what we wind up getting is we get capital X u dot, which that dot is going to represent a derivative with respect to time. So since there's one dot, this means that it's del u del t. So it's u as a function of t, and then we take the derivative with respect to time. So that's what that dot is going to mean for us? So then we have our alpha x double prime, which the double prime will represent a double derivative with respect to the spatial coordinate x. And then we'll just have our u. Now, what we can do is we want to separate these variables such that u is on one side, x is on another side. So what that basically means for us is that we're going to get capital X double prime all over capital X is equal to 1 all over alpha, u dot all over u, and we have to set this equal to some sort of a constant. We make the assumption in separation of variables that this is equal to some sort of a constant. And what we're going to call that constant is sigma squared, the square root of the eigenvalue. Now, what's difficult about this process is that we have to figure out what the appropriate sign for sigma is equal to. Now, you don't necessarily have to make a rash assumption. You can solve this problem with respect to both signs and then figure out which one's the yields a nonsensical solution. So if you were to solve this problem using a positive sigma value, you would find out that the solution doesn't make any sense. Although it does satisfy the conditions that we've given, the solution doesn't make any sense. So we know that we can actually just say that this is a negative, and this will essentially tell us that the transient solution will wind up decreasing with infinite time, which is exactly what we want. So now that we have that, what we can do is we can solve across, and we wind up getting 2. So we get 2 ordinary differential equations that are very, very easy to solve. We wind up getting 2 homogeneous linear ordinary differential equations. So that's very, very simple. And we know just by solving these, I'm not gonna solve these particular expressions. You can go ahead and solve these by means of making the assumption that x and u is equal to e to the, so on, so on. Plug that in, and then you can figure out what the solution is. So essentially what we get is x as a function of x is equal to a cosine sigma x plus b sine sigma x. So that's our spatial expression. With respect to our temporal solution, we know that u as a function of time is going to be equal to some constant, we'll call that c, exponential to the negative alpha sigma squared t. Oh, Facebook status update. Alright. So we now know that our temperature as a function of x and t is going to be both of these functions multiplied together. In order to make this a little bit more simple, what we're going to do is we're going to multiply across, and we're going to say that a and c and b times c is just equal to some constant, because we still have to figure out what those are anyways. So what we wind up getting is the temperature with respect to x and t is equal to x as a function of x, u as a function of t, is equal to, and I'm just going to reuse the variables a and b. So a cosine sigma x plus b sine sigma x e to the negative alpha sigma squared times time. Now I just want to reiterate this point. So this a constant now takes care of both the a and c constants being multiplied together, and this b constant that we've defined right here now takes into account both the b and c constants being multiplied together. So this is just a means of simplifying, and it will not change the solution. So now we can go ahead and we can apply our boundary conditions and our initial conditions. So we know that the temperature at x is equal to 0 for all time is equal to 0. Now we can go ahead and plug that into the expression that we derived above. And we know that at cosine of 0 is equal to 1, sine of 0 is equal to 0. So that basically just means that we get a e to the negative alpha sigma squared times time. We can divide through by our exponential term, and that simply means that for this particular boundary condition we get a is equal to 0. Now what we can do is we can apply our secondary boundary condition, which tells us at x is equal to L for all time t, we get the temperature is equal to 0. So by plugging in a is equal to 0, this simplifies our expression down to b sine sigma L, because we're evaluating x is at L, e to the negative alpha sigma squared times t. We can divide through by our exponential, and then that essentially just gives us b sine sigma L is equal to 0. Now in this particular case we have two possibilities for what we can do. Now what we could do is we could divide by sine sigma L, which would mean that b is equal to 0, which would unintentionally give us an entire solution that t is equal to 0. Now although this satisfies our boundary conditions, this is a trivial solution. Although it does satisfy it, doesn't make any sense. So what we can do is we can say that what we really want is we want to divide through by b, and we want to find a sigma value such that sigma L is always equal to 0. So what we're going to be doing is we're going to be finding the value of the eigenvalue. So we know that sigma L is always going to be equal to 0 as long as it's being multiplied by n pi. So if we have an integer being multiplied by pi, sine of whatever that is always going to be equal to 0. So this satisfies it. So from here we know that sigma is equal to n pi L for n is equal to 1, 2, all the way up to any n value integer. So now we can go ahead and we can plug all this into our solution that we have so far. So we have t, x of t. And now since we have a n number of eigenvalues, we have to add a subscript to our constant, because our constant will change with the eigenvalue. So we have an n number of these b sub n's. We have an n number of those. So we get bn exponential of sigma n squared pi squared all over L squared times time times the sine of n pi all over L times x. And again, that's going to be for n is equal to any integer up to n. So what we can do is we can actually rewrite this in terms of an infinite sum. We can rewrite this as tx of t, n is equal to 1 to infinity. We're going to now call this unknown constant c sub n. We're going to multiply that by our n number of x of t solutions. So essentially all this is telling us is that the infinite sum from n is equal to 1 to infinity of cn times tn, which is going to be our the solution that we previously derived, all over L squared times t sine n pi L times x. So now we have this, but we still need to figure out what c sub n is equal to. So we can use our initial condition in order to figure this out. So we're going to use our initial condition. So we know in terms of our initial condition, for all x at time 0, it's going to be equal to some generalized function of x. So plugging in time is equal to 0, the exponential drops to 1, and we get the infinite sum from n is equal to 1 to infinity of c sub n sine n pi all over L times x. So, how are we going to figure out what c sub n is? Now what we can use is we can use orthogonality to assist us in figuring out what our c sub n is. We're going to multiply both sides by a similar function, which is going to be sine of m pi over L times x. And we're going to utilize orthogonality to make sure that our sine n pi over L times they're orthogonal functions. And we're going to utilize that in order to figure out what our c sub n is equal to. So by doing this, we want to integrate about the entire bar from 0 to L. And we have our function f of x sine times m pi all over L times x. We're going to integrate that with respect to x. And we're going to set that equal to the integral from 0 to L times the infinite sum from n is equal to 1 to infinity c sub n sine m pi over L times sigma, times x, times the sine of n pi over L times x. We're going to integrate that with respect to x, and we're going to do this for n is equal to 1, 2, 3, all the way up to some value n integer. And we also need to note that this is also for some m integer. So what we can do is we can utilize orthogonality to assist us in figuring out what the c sub n is. So we know using orthogonality that the integral from 0 to L of sine m pi L times x times the sine of n pi L times x dx is going to be equal to two things depending on what we assign m and n to be. So if we make it such that n does not equal m, it's equal to 0. However, if we decide that we want n to be equal to m, the integral will be equal to the length of the rod divided by 2. So we can go ahead and we can plug this in to our previous expression. So we want to utilize this right in here, and just go ahead and plug that in. And based on that, we now know that c sub n is equal to 2 pi L. Again, this is just plugging it into our previous expression like the arrow indicates. And then you can go ahead and solve for c sub n. So we get 2 over L, the integral from 0 to L of our generalized temperature function f of x times the sine of n pi all over L times x dx. So now we know for any given n, we know exactly what c sub n is equal to. So with that being the case, we've actually completed our problem. So we can write out the solution in summary. So, in summary, we have derived the following for our temperature function. So our temperature is a function of x and t. For this simple rod example, it's a Fourier rod. We know that the temperature distribution is an infinite sum from n is equal to 1 to infinity of c sub n, the exponential of negative alpha, n squared, pi squared, all over L squared, times time, multiplied by the sine of n pi L times x. And we have to define what our constant is, where c sub n is equal to the evaluation of this integral that we evaluated by means of our initial condition and by using orthogonality in order to assist us to figure this out. So n pi all over L times x dx. So now that is our completed solution. So our temperature distribution as a function of space and time is equal to the what we've defined there. And that's the solution to this particular problem. Now, if you didn't have zero boundary conditions, and let's say you wanted it equal to be some temperature T1 or some temperature T2, then this becomes a little bit more complicated, and you have to establish that you have a transient and a steady state solution, and then you pretty much follow the same process. If there's any interest in me solving a problem like that, I'd be more than happy to. Hopefully this has assisted you in figuring out how to solve a Fourier rod problem that we've defined previously. So let's just do a quick summary. So we utilized our heat conduction equation, and we broke that down into the spatial and time coordinates that we want. So we've derived this particular expression here. Then by means of utilizing the boundary conditions and the initial conditions, we figured out, after using separation of variables, what our unknown constants A and B were equal to. Or, sorry, A and then our eigenvalue sigma is equal to. From there, we utilized a property that allows us to turn all of these solutions into an infinite sum, and we defined a new characteristic constant C sub n. From there, we utilized our initial condition, and then we utilized orthogonality in order to tell us what C sub n is equal to. So once we figure out what C sub n was equal to, our solution was complete, and we now know how the temperature distribution changes with respect to space and time for this particular problem. Again, hopefully this has helped assist you in any way. If there's any open-ended questions, or while describing this I said something incorrectly, please let me know. If there's any more questions, I'd be more than happy to answer. And thank you very much for listening.